Welcome back. Now, in this section we are starting with the space time correlation function. So, first thing we have to define for any system of n particle, what is the number density at position r and time t. So, this is the formulation as you see on your slide, n r, and as you know the line at the bottom is saying that it is a vector dot r. So, this is the time. So, these are the r and t. So, r and t are the two functional, and if you look at 1 over square root of n is providing you the factor that is going to normalize it, and then you are looking at delta r minus r r t at any time t, and you are looking at this change in the r, that means the positions of the particle, and now you are looking at summation over all the particles and dividing it by square root of number of particles. That is where you get the number density with respect to time. So, with that, and now we know that with the thermal average n r t is equal to under root of n over v, which is the total volume. So, the autocorrelation density, which we call the density correlation function, is created by g. Now, g is called density correlation function, which is g r minus r dash t minus t dash. So, now we are looking at original position to another position r dash, and original time t or the beginning time t and ending time t dash. And then we are looking at the volume, because now it is related to the volume, and that is where delta n r t at the original time r and t, and then at time r dash and t dash. So, now you can see that this is the density correlation. So, density at time original time, let us say t 0, at any arbitrary time t. Now, you are looking at the density at time t, but now density has space and time. This is where it becomes space time correlation function. It is not only dependent on the time alone, but it is also dependent on the position of the particles, and that is what makes a whole lot of difference in density correlation function. And this is why it is such an important correlation, primarily because it tells you how the positions of the atoms will change with respect to the time, and then what is the transport coefficient there. We are going to look at those transport coefficient coming out of neutron scattering. So, if you look at a large particle and you bombard them with neutron in a research nuclear reactor, and this is why research nuclear reactors are created, where you create a beam of neutrons, and then you do experiments with the beam of neutrons, and that beam of neutrons essentially then gives you a scattering experiment, diffraction experiment, as well as inelastic scattering experiment as well. So, this is where you can now look at all these parameters which are provided by density correlation function. So, now if you look at density correlation function here on your slide, now we can write complete expression, which is essentially in terms of now positions. So, position at time t 0 r t r at time t 0, and then arbitrary time t, and this is the change in the position after time t, minus n, which is n is the density expression. So, now you are looking at g r t as 1 over n, which is the density, number density, and then the time correlation function of the positions minus the density of the overall system. Furthermore, we can take r 0 is 0 without loss of generality. So, if you look at r 0 at the origin, we are starting at the original point, then all we are left is the change in the particle over time t, if we consider that is starting at the position 0, and that origin can be arbitrarily defined. So, that you can say r 0 is 0, and now all you are looking at g r t, which is the density correlation function. Again, you sum over all particle I is equal to 1 to n, and now if you look at the position, what we call is position over time period. So, we are looking at the average position changes as you move in in the system, that is where you have average density of position at r and t, given that the atom was at origin at time t 0, and that becomes a correlation itself, because the original point is at time t 0 and at the point 0. So, now if you look at the density correlation function contribution, there are two parts of it. One is G s, where the particle is moving around and you are looking at it from the original position, but then there is also relative position of that particle with in terms of the other particles in the system. Describe the, so if you look at G s, so there are two parts of it. Describe the motion of tagged particle as it moves through the fluid. So, look at one particle, tag it and see how it is moving through the fluid. Other one is describe the motion of the particles relative to another particle. So, now we are looking at the relative motion of the particle, which is called G d, which is connected with some of the density, but if you look at they describe the motion of tagged particle and how it is moving out, then you are looking at the structure of the system, and that is where G s r t and G d r t are the two contribution, and you want to look at both, and the summation of the two is the total density correlation function. So, if you look at the sketch here, you are looking at two situations, a particle which is tagged, how it is moving through this small circle, and that is the G s r t, and if you look at the other particles and their relative motion with each other, that becomes G d r t. So, that is where you differentiate between different correlation contributions, and they become important, because when you are doing correlation and if you are doing with the tagging of the particles, then you have structure factor understanding lot more clearer, and then you also look at the density function. So, that is where you use the Fourier transform of G r t, that is where you get the dynamic structure factor. And the reason we call it structure factor, because that is the property that you can calculate, you can obtain from the neutron scattering experiments and neutron diffraction experiments, particularly for the structure factor. Neutron diffraction experiments will give you the positions of the particle at different temperature and pressure conditions. So, if you look at the dynamic structure factor, how these particles are moving with respect to time, which is k omega, where omega is their frequency of motion and k is their essentially dependent on the their crystal structure. Now, you are looking at the dynamic structure factor, which is the double Fourier transform of the two density correlation functions. So, if you now understand there are two different density correlation function, which is one is d s and d g s and g d. So, if you go back, these are the two contributions. If you take Fourier transform of both of them and you saw this double Fourier transform, that gives you dynamic structure factor. But this is also connects with the position of the particles, which we looked at earlier in terms of G of r, which was radial distribution function. If you remember our discussion of G of r, then we understand that you can take different shells of particles, take a central position and go away radially outwards, and then you look at different shells how many particles you find. So, those become nearest neighbors. The first nearest neighbor, second, third and fourth neighbor, those are different shells as you move spherically outwards from the central atom. So, if you look at that is and you sum them up over n number of such particles using molecular dynamics positions calculation, then you get radial distribution function. And so, if you take the Fourier transform of that, because you are looking at this this particular snapshot and not the dynamics of it, it is called static structure factor. So, the first Fourier transform, the single Fourier transform obviously provides you static structure factor, but when you add the dynamic density correlation function, then you have dynamic structure factor. And the reason I am providing you this information, because the time correlation function and the Green-Kubo formulation, where essentially it connects the time correlation function of any particle, we can extend this Green-Kubo formulation into the what we call is dynamic structure factor by now utilizing the density correlation function, which is space time. So, it is not only the time, but the space time correlation function. So, now if I take a particular material and bombard it with some, let's say, different kinds of radioactive active substances, there will be knocking off of some of the particles, and the particle density will change under the radiation effects. So, think about the radiation chemotherapy. When you do, there is a heavy radiation coming through, and some of the atoms in your body in the cell are knocked off, and if you want to look at the changes in their density and their structures, then you can use something like dynamic structure factor there. And so, and again we are simulating that in a particular molecular dynamic system to understand what actually happens inside human being when they are exposed to the radiation. So, I would then create a simulation of hydrocarbon type with a single human cell, and then I can provide a radiation with certain kinetic energy, and then look at how the density changes, or what happens, what changes take place in this hydrocarbon change, or let us say the nucleus of the human cell, which also has DNA and all of that other material in it, genetic material. So, now these are the things that you can obtain using dynamic structure factor. Also important factor, there is static structure factor, which connects with the diffraction pattern. If you look at the X-ray diffraction, and if you look at a particle, let us say a sheet of metal, and let the X-ray go through, you will see that you can see the atomic positions, and those atomic positions are the static atomic positions at particular time t, because it is a snapshot. So, if I take successive such X-ray diffraction pattern, I may see the mobility, but if I just want to look at that average positions of the particle, which is g of r, radial distribution function, then I can take the Fourier transform of that, and then we can get what is called static structure factor. So, I will now show you a case study where we can move into some of these effects and how we calculate that. Thank you.